Hello everyone, welcome to College Algebra Lecture 14. And in this lecture we're going to focus on section 11.1 in your textbook, which is on systems of linear equations, and in particular we're going to focus on equations that just involve two variables. So it'll be two equations by two unknowns, and typically those unknowns will be x and y. Okay? So what do I mean by a system of two linear equations and two variables? Well, something like this. If I have, say, 3x minus y equals negative 5. Let's say that's one linear equation, so that's one equation of a line. And then say 4x plus 2y equals 6. That would be another linear equation. So together they form a system, right? So this is a system now of two linear equations. Now, we're going to try and solve these. So what does it mean to be a solution? Well, a solution to a system of two linear equations is an ordered pair, right? A point or an ordered pair that satisfies both equations. If you plug that point in to both equations, you get true for both of them. So it's an ordered pair that satisfies both, and that's important, both equations. Okay, let me underline that, both equations. Now, it turns out there's several types of linear systems. So one type, and this is really the most common type. So let's say types of linear equations. So you could have a situation where we have the two lines and they cross at one point. And again, this is going to be the most common case. So let's say this is first linear equation and this is my second one, let's say. So in this case, right, they both intersect right there. So that point, that ordered pair, is going to satisfy both equations. Right? So we say there's exactly one solution. And for the system itself, we can say it's an independent. So independent system. That's going to be the most common case. So they intersect at one point, so there is a solution. And there's exactly one solution. Okay, another possibility is that the lines could do this. Right, they could be parallel. So what does that mean? Well, if the lines are parallel, it means that they never cross, right? So there can't be any point that satisfies both equations. So there's no solution. And as a system, we call this an inconsistent system. So inconsistent system means there's no solution. It means the two lines are actually parallel. And then the third possibility is this. Let's say we have the first line, and let's say the second line is right on top of it. It's hard to draw on top, I'll just draw it next to it. Let's say it lies right on top of that first line. So in this case, since every point, right, is a solution to both of those lines, then there's an infinite number of solutions. And this is called a dependent system. So again, what's going on here is really, it turns out that those two equations were really the same line. Right, so I'll say same equation, same line. That means there's an infinite number of solutions, because every point on that, every point here, point here, point here, every point is going to satisfy both equations because they really are the same equation. And then as a system, this is called a dependent system. Okay, so again, those are the three possibilities. The most common one is going to be that first case where the lines cross at exactly one point. Okay, so let's do a problem. Let's see, how do we determine whether a particular point is a solution to a system? Well, we can just plug it in, right? So let's say we're given this problem, determine whether the point 8, 5, that ordered pair, is a solution to this system. 5x minus 4y equals 20, and then 2x plus 1 equals 3y. Well, all I have to do is plug it in to both equations, and it has to satisfy both of them. So let me try the first one. So remember, this is always x, y, right? So in the first equation, I have 5 times 8 minus 4 times 5. And I'll put a question mark here. Does that equal 20? Well, 5 times 8 is 40, right? Minus 20 equals 20. Yep, 20 is equal to 20. Right, left-hand side is 20, right-hand side is 20. So that checks. Then if I try the second one, I have 2 times 8 plus 1 equals 3 times 5. So this is what, 16 plus 1, so 17 equals 15. No, right? That does not work. So since that point does not satisfy both equations, it is not a solution. So 8, 5 is not a solution to that system. Okay, we got true here, but we got false here. We'd have to get true for both of them. It has to satisfy both of them. Okay, so that's really all you need to do. Very straightforward, right? Just plug in the point to determine whether a particular point is a solution to a system. If it satisfies both equations, it is a solution. If it doesn't, then it's not a solution. Let me do another example. I'll just make one up. Let's say I want to determine whether the point -2, 3 is a solution to this system. -3x plus 4y equals 18, and then x minus y is equal to -5. Okay, so let's check it. I'll plug it into the first one. So I have -3 times the x value, which is -2, plus 4 times 3. Does that equal 18? Well, this is 6, right? Plus 12. Yeah, 18 equals 18. So that's true. Right, so that works. And if I try the second one, I have -2 minus 3. Well, that's -5 equals -5. That's also true, right? That works. So therefore, is that point a solution? Yes. Yes. -2, 3 is a solution to that system. Okay, so now let's talk about how to solve systems of linear equations and two unknowns. There's several ways we can do this, right? One of them is by graphing. We could just graph these, and if there's a solution, we will see where the two lines intersect, right? So one solution is by graphing. So solving systems of equations by graphing. So let's say I want to solve this system. Y equals 3x plus 1 and 2x plus y is equal to 4. So there are my two linear equations I want to solve by graphing. Okay, so let's try this. So x, y. So what I'm going to do is I'm going to create a table for each of those equations. So if I look at the first equation, x, y. This is the one, y equals 3x plus 1. I only need 2 points. Let me pick some easy x values. Let's say x is 0, then y would be what? Y would be 1, right? And if x is 1, y would be 4. So I'll plot 0, 1 right there, and then 1, 4 be right here. So this line looks like this. Okay, and then I'll do the second equation. So this is the 2x plus y equals 4. So again, pick some easy points. Maybe if x is 0, it looks like y is going to be 4. Right? If I plug in a 0 for x, so I have 2 times 0, 0, plus y is 4, so y must be 4. And then maybe let's just do the intercepts. So that was sort of the y-intercept. If I want to find the x-intercept, I'll make y 0, then x must be 2. Right? You can work it out if you need to. You can say 2x plus 0 is equal to 4. So then I have 2x is equal to 4 divided by 2. So x is equal to 2. So 2, 0. So if I plot those 2 points, 0, 4 is here, and then 2, 0 is here. So this graph looks like this. Okay, so here is, I'm kind of illustrating the problem with graphing, right? There's a solution, right? Because the two lines intersect. They intersect at this point. I'll do it in green. So they intersect at that point right there. But the problem is, it's difficult, especially with drawing this by hand, it's difficult to figure that out, to figure out what those coordinates are. I'll say it's difficult to determine this point. Now, one thing we could do is we could graph this, using technology like Desmos and see if we can get a better result. Actually, let me try that and see what we come up with. So here I actually did that problem again, but using Desmos. I plotted the two lines using Desmos. And here we can see that they intersect at the point 0.6, 2.8. So x equals 0.6, y equals 2.8 is the solution to this system of equations here. So the solution again is x is equal to 0.6, y is equal to 2.8. Okay, so graphing is one possibility. It's not very accurate, right? I had to actually use Desmos to figure this out. I couldn't do it by my hand-drawn figure, it just wasn't accurate enough. If the solution happens to be, both integers, you might be able to do it graphing, but there's better ways. There's other techniques that we're going to talk about now that will give you exact answers, okay? So let me talk about the first of those, which is called substitution. Okay, so let's say we want to solve a system of equations by this method, which is called substitution. So here are the steps. The first step is you solve for one of the variables in one of the equations. Typically, you would choose the easiest equation to solve for one of the variables, either x or y. Usually it's x or y, right? They could be named anything, though. Second, once you do that, you want to substitute the expression for this variable into the second equation, then solve for the remaining variable. Right? When you substitute it in, you're going to have just one equation in terms of one variable. You can solve for that remaining variable. And then when you have the solution to that one variable, you can substitute that solution into either the original equations to find the value of the first variable. Okay, so it sounds like a lot. Let's do a few examples, and it'll make a lot more sense when we do some examples. Let's say we're asked to solve this system, and we'll solve by substitution. So I have x plus 2y equals -9, and then 7x plus 4y is equal to -43. Okay, so again, the first step was to solve for one of the variables in one of the equations. So if we look at this, right, we have our two variables are x and y. I can solve for either x or y in the first equation or x or y in the second equation. Now the easiest would probably be to solve for x in the first equation because its coefficient is already a 1, right? So I'm going to solve for x in the first equation. You should always just solve for the easiest variable, okay? So to do that, I need to subtract 2y from both sides. So then I'm going to have x is equal to -2y minus 9. Okay, so step 1 is done. Now here's where the substitution comes in. I substitute this expression, so this entire expression, into the second equation. Where I have x, I'm going to plug in -2y minus 9. So 7 times x now, but x is the same as -2y minus 9. Equals -43. Now notice this equation now is just in terms of one variable, right? It's just in terms of y. So we can solve this for y. So I'll distribute the 7. So I have -14y. 7 times -9 is -63. If I combine like terms, well, -14y plus 4y is -10y. And then I'll have to add 63, right, to both sides. So I'm going to get -10y is equal to 20. And then if I divide by -10, I'll have my solution for y, right? I get y is equal to -2. Okay. So now that I have one of my variables, right? I have one of the answers, one of the solutions. Y is -2. I can plug it back into any of the original equations and solve for x. So what's the easiest equation to plug into? Well, if you think about it, right, I could use this equation, this one, or I could use this one because this is just the first equation that I manipulated, right? And this is probably the easiest because it already has x equals, right? It's already set up to solve for x. So I'm probably just going to plug back into that last equation. So x equals minus, so -2 times y, but y is -2, minus 9. So then this is going to be 4 minus 9, right, which is a -5. So I just found that x is equal to -5. And then if you want the point at which those two lines intersect, well, it's going to be the ordered pair, right? -5, comma, -2. Right? Because it's always x comma y is the ordered pair. Okay, let's try another one. So again, solve by substitution. Let's say this is my system. 4x plus 3y equals -9. And then let's say y equals 5x plus 16 is my second equation. Okay. So this is nice, right? Because step 1 is already done for us. The second equation is solved for y, right? I have y equals 5x plus 16. So immediately I can go to step 2, the substitution step, and I can go to the first equation, and where I have a y, I can plug in this y, which is that expression. So I go to the first equation, and where I have a y, I'm going to substitute in 5x plus 16. Okay, and now I can solve this equation for x, right? So I'll distribute the 3. So I have 4x plus 15x plus 48 is equal to -9. I can combine like terms, right? So this is 19x plus 48 is equal to -9. And then I need to get rid of that 48, so I'll subtract 48 from both sides. So 19x equals -57. And then finally, I can divide both sides by 19. And it turns out that 57 divided by 19 is 3, right? So this is going to be -3. And now I have to figure out y. Well, I can figure out y by plugging x back into one of my original equations. What's the easiest equation to plug it into? The second one, right? Because it says y equals. So it's already set up to solve for y. So 5x plus 16. So y is equal to 5x, but x is now -3 plus 16. So y is equal to, this is -15 plus 16. So it looks like y is equal to 1. So the solution is going to be the point, or the ordered pair, -3, comma 1. Okay. Now, you got to be a little careful. You could end up having some problems, and where we don't actually get a solution, or we get an infinite number of solutions. Let me mention how those will appear if you're trying to solve something using substitution. So let's say this is my system I'm trying to solve. So these are sort of like the special cases. Normally you get an x and you get a y. You get one point at which the lines intersect, but sometimes you don't. So let me look at those other cases. Okay, so again, I want to solve this by substitution. I could just divide by 4 in the second equation, but then I have fractions. Let me solve for y in the first equation, because I want to solve for one of the variables and one of the equations. So I'm going to choose to solve for y in the first equation. So I need to subtract 3x, right, from both sides. So I have y equals -3x plus 5. Now I'm going to substitute that into the second equation. So where I have y, I'm going to plug in -3x plus 5. If I distribute the 4, then I get -12x plus 20 is equal to 18 minus 12x. And now if you try to get the x's onto one side, look what happens. If I add 12x, I add 12x, x terms are going to disappear, and I just get 20 is equal to 18, right? Which is obviously false. This is never true. This is false. By the way, you could even go further, and you could say, like, let me subtract 20 from both sides. And you could always put 0 on one side, so you have 0 equals -2. But same thing, this is always false. So what does that mean? If you try to solve it using substitution or later using elimination and you get something that's false, that means that there's no solution. So what does that mean in terms of the lines? It means that the lines are parallel, right? They never cross. And what does that mean in terms of a system? It means, if you remember, it's an inconsistent, is what we call it, inconsistent system. Okay, here's the other special case. What if I'm asked to solve 2x minus y is equal to negative 6, 4x minus 2y is equal to negative 12. Let's say that system. So again, let me solve the first equation for y. That'll probably be the easiest. Actually, to make this easier, to make it a 1y, I'm going to move the y to the right-hand side, so I'll add y to both sides. And then I just need to add 6, right? Add 6. So then I'm going to get y is equal to 2x plus 6. But then, of course, I can write it this way. Y equals 2x plus 6. If they're equal, it doesn't matter what side you write each expression on. You can switch the sides. So now I go to the second equation, and where I have a y, I'm going to substitute in 2x plus 6. Okay, so if I distribute into negative 2 now, I get 4x. This is going to be negative 4x, right? Negative 2 times 2 is negative 4. And then negative 2 times positive 6 is negative 12. So if I simplify, the 4x's are gone, and I get negative 12 is equal to negative 12. Or again, you could always write it as 0 equals something. In this case, if I add 12 to both sides, I'm going to get 0 is equal to 0. Either case, either negative 12 equals negative 12 or 0 equals 0. This is always true. Right, so what does that say in terms of solutions? It means there's an infinite number of solutions. In terms of the graph, it means that those two equations really represented the same line. So say these are the same line. They're right on top of one another, so these are the same line. And in terms of a system, remember it's a dependent system. This would be the case of a dependent system. Okay, and again, it's because we got 0 equals 0 or negative 12 equals negative 12, something that was always true. Okay, so that's the substitution method, and we can do a bunch more examples in lecture. Now let's talk about the last method, which is the elimination method, or some books call it the addition method. So let me write that out. Okay, so if we want to solve systems of two linear equations and two unknowns using elimination, or again, some books call this the addition method, then these are the following steps. Okay, I'll walk through the steps, and then it'll make more sense when we start actually doing examples. You'll see where all these steps come into play. So the first step says write both equations with the x and y variables on the left-hand side and the constants on the right-hand side. And then we're going to line up the x variables and line up the constant, or line up the x and y variables and then line up the constants. Now the goal here is to get opposite coefficients on one of the variables, either x or y, such that when you add them, you get 0, right? That's where the elimination comes in. So the goal is to get opposite coefficients on one of the variables for the two equations. And sometimes you may need to multiply one or both of the equations by a particular value, by some constant, to achieve this. Then once you've done that, you can add the equations together. It'll eliminate that one variable, and now you can solve for the remaining variable, right? So you'll end up with just one equation, one unknown. You can solve it. And then just like before with the other method, now that we have one solution, we can plug it back in to one of the original equations and solve for the other solution, for the other variable. Okay, so again, it sounds a little confusing. Let me do some examples and walk through like each of these steps. Let's say this is my system that I want to solve. So 3x minus 3y equals 12, and 2x minus 6y is equal to 4. And I want to solve it by elimination. Okay, so by this elimination technique. Okay, so actually the first step we've done, right? So the x's and y's are on the left-hand side, the constants on the right-hand side. The x's are lined up in a column, the y's, and then the constants are lined up on the right-hand side. So the first step is done. Now look at the second step. The goal is to get opposite coefficients on one of the variables. So if we look here, we could try and get, like usually what you use is what's called the lowest common multiple, right, of the two coefficients. So 6 would be the lowest common multiple. I could try and make one of these a -6 and one of these a +6, and that will allow me to limit the x variables. But you should do whatever is easier. Now look at the y. See how I have a -6 here? If I can make this a +6, right, this coefficient in the first equation, then I can add them and get rid of the y's. So that means only adjusting one of these equations, right? I only have to multiply one of the equations by a particular constant. So let's do that. Let's try to make this a +6. Let me write that here. So this, we would like to be, do a little better. So would like this to be a +6, right? So to make that a +6, right now it's -3, we can multiply by -2. So I'm going to multiply that entire first equation by -2, both sides. And it's a common mistake to forget to multiply the right-hand side, so make sure you don't forget both sides by -2. Okay, so now I can distribute into -2. So I have -6x plus 6y is equal to -24. So it's the same equation as before. I just changed it slightly by multiplying both sides by some constant, right? It doesn't change the graph of it. It'd be the exact same linear equation. But now I have a +6 in the location that I want it to be in, right? So now the second equation I can write down again underneath it. We didn't have to multiply that by anything. And now I can go to step 3, which is where I do the addition, right? Where I actually add to eliminate. So if I add these together, +6y minus 6y by design disappears. I have -6x plus 2x, which is -4x. And on the right-hand side, I have -24 plus 4, which is -20. So then I can divide both sides by -4. And I'm going to get x is equal to +5. Okay, so I'm half done, right? I have the x value. How do I find the y? Well, I need to plug this into one of the original equations. Does it matter which one? Nope, doesn't matter. You should choose the easier one. In this case, either one is probably equally as difficult, right? So maybe I'll just plug it back into the first equation. So I have 3x minus 3y equals 12. So for x, I'm going to plug in 5. So this is going to be 15 minus 3y equals 12. I'll subtract 15. I'll finish it over here. So I have negative 3y is equal to negative 3. And then I need to divide by negative 3. Right? That'll cancel, so I get y equals, and then negative 3 divided by negative 3 is positive 1. And that's my solution. So if you want the ordered pair, it would be 5, 1. X is 5, y is 1. Okay, here's another example. Let's say we want to solve this system. Okay, so first thing, it's already lined up, right? We don't have to move anything from one side to the other. My x's are lined up, my y's, and then my constants on the right-hand side. That's good. Okay. I want to eliminate one of the variables, right? In this case, one is not necessarily easier than the other. Let's say we want to eliminate the x. So let's eliminate the x. So to do that, right now I have a negative 4 and a negative 3. Well, I know that the lowest common denominator, or I'll do it as lowest common multiple. Sorry, the lowest common multiple of 3 and 4 is equal to 12, right? It's the lowest number that 3 and 4 go into evenly. So one of these coefficients I want to make a negative 12, and the other one I want to make a positive 12. Let's say I want this one to be a negative 12, and I want this one to be a positive 12. Because then when I add them, the x's will disappear, right? So how do I make that first coefficient a negative 12? Right now it's a negative 4. What do I need to do to make it a negative 12? I need to multiply by positive 3. So I'm going to multiply the first equation by positive 3. Again, don't forget the right-hand side. So then this is going to be negative 12x, right, plus 6y is equal to 18. And then the second equation, I want to make it a positive 12. Right now it's a negative 3, so I guess I need to multiply it by negative 4. And again, I have to be careful here, right? I can't forget to multiply the right-hand side also by negative 4. So if I distribute the negative 4, this is going to be 12x. Negative 4 times negative 5y is plus 20y. And negative 4 times negative 28 is positive, I guess it's 112, right? 112. Okay, so I've rewritten those equations. They're still the same equations, they're just rewritten. Right? They still have the same solution. And now I'm just going to write them again on top of one another. Okay, good. So now we can add them. That gets rid of the x by design. I end up with 26y is equal to, what's that, 130? And now to solve for y, I need to divide by 26. So y equals, and it turns out 130 divided by 26 is exactly equal to 5. So nice, easy integer answer there. So the y is 5. How do I go back and find x? I simply plug y equals 5 back into one of those original equations, right? Back into one of these initial equations here. So let's just maybe use the first one. So I have negative 4x plus 2y equals 6. So now I want to plug in 5 for y. So I'm going to get negative 4x plus 10 is equal to 6. Need to subtract 10. So I have negative 4x is equal to 6 minus 10 is negative 4. And then finally, if I divide both sides by negative 4, I'm going to get x is equal to 1. So my solution, if we want to write it as an ordered pair, is 1, 5. Okay, what about this one? Let's say I have 2y equals negative 4x minus 18, and then 8x plus 4y equals negative 36. Okay, well, first thing, I need to write them so that the x's are lined up, the y's are lined up, and the constants are lined up on the right-hand side, right? So let me take that first equation and move the x term to the left-hand side. So I can do that by adding 4x, right, to both sides. So this becomes 4x plus 2y equals negative 18. And the second equation is fine, so I just have 8x plus 4y equals negative 36. Okay, let's say we want to eliminate the x's again. So if this is a positive 8, I want this coefficient to be a negative 8, right? The lowest common multiple of 4 and 8 is 8, so I can leave that bottom one as positive 8. So I only need to correct the first equation. How do I make that a negative 8? Well, I can make that a negative 8 if I multiply the entire first equation by a negative 2, right? Because I have a 4 right now, and negative 2 times 4 gives me a negative 8. And again, don't forget also the right-hand side. So I have negative 8x minus 4y equals positive 36. And in the second equation, I'll just write down again, 8x plus 4y equals negative 36. Now, if we do the next step, which is adding, look what happens. The x's disappear, the y's disappear. So I have 0 equals, in this case, it happens on the right-hand side. Also, I also get 0, right? 36 plus a negative 36, or 36 minus 36 is also 0. This is always true. Right? If I gotten like 0 equals 6, that would be always false. But if I got 0 equals 0, that's always true. And remember what that means. It means that those two lines are actually the same, right? So it meant, in terms of solutions, it means there's an infinite number of solutions. The two lines are really the same, right? They're the same line. And remember, we call that a dependent system. Okay, so that's like a special case. And the other special case would be if you got like 0 equals negative 4, 0 equals 7, or something that's always false. That would mean the two lines are parallel and there's no solution. Okay, I want to do one more thing in this section. I just want to do a couple of applications. So a couple of word problems involving systems of equations. And I'll just do 2 just to give you an idea of this, a feel for this. Okay, so this problem says the admission fee at an amusement park is $2.75 for children and $5.20 for adults. On a certain day, 270 people entered the park, and the admissions fees collected totaled $1,061. And the question is, how many children and how many adults were admitted? Okay, so how do you start this? Well, the first thing we have to do is give a name to the variables, right, that we're looking for. Like, give some variable names. So what are we looking for? We're trying to figure out how many children and how many adults attended this amusement park. So maybe, I mean, you could use X and Y, but maybe to make it more applicable to this problem, let's maybe call A the number of adults, and maybe C the number of children. Okay, so give variable names to your unknowns. So A is the number of adults, C is the number of children. Now we need to, number of children. Okay. Now we need to come up with, it's going to turn out to be two linear equations by two unknowns, right, in terms of A and C. So if you look at that first sentence, it says, on a certain day, 270 people entered the park. So what that means is the total number of adults and the total number of children, they had to sum together to give you 270. So isn't that the same as the equation A plus C, right? Number of adults plus number of children must equal 270. And then the last part of that sentence, I can come up with my second equation. It says, and the admission fees collected totaled $1,061. So we need to figure out, well, how much was collected from the adults and how much was collected from the children. If I add those together, I should get 1,061. Well, if each adult is paying $520 and each child is paying $275, then one way I can write this is the total amount of money collected by the adults must be $5.20 times the number of adults, right? So 5.20 times A, that'll be the total amount of money collected from the adults, plus, and then the total amount of money collected from the children must be $275, right, dollars per child times the number of children. That's got to give me the total amount of money collected from the children, and that's got to equal 1,061. You guys see that? So now I have two equations by two unknowns, right? They're two linear equations by two unknowns. So I can solve this by using substitution or elimination. Probably want to use elimination, but it doesn't matter. You can use either. Let's just solve it using elimination. Okay, what I'm going to do first, just to make things a little easier so I don't have to deal with decimal values, is I'm going to multiply that second equation by 100. Just to clear out all the decimals, and then I won't have to worry about having any decimal values. And don't forget to multiply the right-hand side, right, also by 100. You can always multiply an equation by anything, and it won't change the solution of that equation. So this becomes 520A plus 275C, right? If I multiply by 100, it's going to move that decimal place 2 places to the right, and that equals 106100. Okay, it's really the same equation, it's just written in a different way, and it's not going to change the solution to that system. The second equation I can just write over again. Or actually, it was the original first equation, but I'll write it underneath. Right? It doesn't matter the order either. Okay, if we're going to eliminate, then I probably want this coefficient, which is now a 1, right? I probably want that to be a negative 520. Because then if I add the a's, I can get rid of the a's. So how do I make that a negative 520? Well, I need to multiply the entire second equation there by negative 520. And again, don't forget the right-hand side. Okay, so if I do that, right, I'm going to get negative 520a minus 520c is equal to, and this is like negative 140,400. So 140,400. The other equation is the same. I can write it down again. In fact, again, it doesn't matter what order, so I'll just write it underneath. So that we don't need to adjust at all. Okay, so now I can add the equations together. By design, my a's are gone, right? If I add negative 520c plus 275c, I'm going to get negative 245c. And if I add the right-hand side, I'm going to get negative 34,300. Okay, so to solve for c, I'll divide both sides now by negative 245. And I get c is equal to turns out to be 140. So I know that, remember, C is the number of children, so there's 140 children that attended. How do I figure out the number of adults? Well, I plug C back into one of the equations. What's the easiest equation to plug back into? Probably that original first equation, right? A plus C is equal to 270. So now I know C is 140. I can plug that in. So if I subtract 140, subtract 140, I'll find that A is equal to 130. Remember, that represented the number of adults. So it was 130 adults. So that's the answer to my question. 130 adults, 140 children. All right, let's do one more application. Okay, so in this example, right, this problem, we're told if Ricky has 13 quarters and dimes, so in other words, 13 coins in his pocket, right? Some are quarters, some are dimes. And if they have a combined value of $2.20, how many of each coin does he have? So how many quarters and how many dimes does he have? Okay, so remember, the first step is to choose some variable names to represent the unknowns, the things that we're looking for. Well, we're looking for the number of quarters and number of dimes, right? You could use X and Y, that would be fine, but it might be more meaningful if we use something, maybe say Q, to represent the number of quarters, and maybe D to represent the number of dimes. Okay, now we're going to try and come up with two equations involving Q and D. So we have two linear equations by two unknowns that we can solve. Well, the first part of the sentence, it says Ricky has 13 quarters and dimes in his pocket. So he has 13 coins total. That must mean that the number of quarters, right, so Q, plus the number of dimes, D, that has to equal 13, right? And then we're also told that they have a combined value of $2.20. So somehow we have to use that information to create the second equation. Well, what are quarters worth? Quarters are worth 25 cents, right? $0.25. So the total amount of money I have from the quarters must be 0.25 times the number of quarters. Right? Does that make sense? So like if I had 4 quarters, 0.25 times 4, I'd have $1 coming from the quarters. If I have 8 quarters, then it would be $2 coming just from the quarters. But in general, it'll be 0.25 times the number of quarters. And then how much money do I have coming from the dimes? Well, it would be 0.10 times D, right? Because each dime is worth 10 cents or $0.1. And that's got to equal the total amount of money, which is $2.20. Okay, so that's it. So we have our two equations by two unknowns. Now, the probably the easier part now, right, is actually solving it. The hard part is coming up with those two equations, coming up with this system. What I would do, just so I don't have to worry about decimals, is again, multiply that second equation by 100. It's not going to change the equation, but it'll just make it easier. So deal with decimals. So this will be 25Q plus 10D is equal to 220. And the other equation I could just write down again. I'll write it underneath. It's not going to change. Okay, now what do we want to eliminate? It's sort of set, I mean, we could use substitution, but eliminate, it's sort of set up for elimination already, right? The Q's are lined up, the D's are lined up, the constants are lined up on the right-hand side. Let's say I want to eliminate, the D's, right? Just to change it up a little bit. So if this coefficient is a positive 10, right? And right now this coefficient is just a 1. Well, I like to make this one, I'll do it in green again. I like to make this a negative 10, right? If we can somehow make that a negative 10, then when I add them, I can get rid of the D's. Well, I can do that fairly easily if I multiply the second equation, both sides, by negative 10. So this is going to be negative 10Q minus 10D is equal to negative 130. Okay, and then I'll write down the other equation again underneath it. The order doesn't matter, so I can keep flip-flopping these. Okay, now I can add, right? By design, these are gone. Negative 10q plus 25q is what, 15q. And then negative 130 plus 220, I guess, is 90. So then if I divide by 15, then I'm going to get q is equal to 6, right? So that says that there's 6, remember q represents a number of quarters. So there's 6 quarters. How do I go back and find the number of dimes? Well, I plug q equals 6 back into one of the original equations. What's the easiest one to use? Probably the q plus d equals 13. Right, so I now know q is 6. So I can plug that in. And then solve it for d, that's easy. I just subtract 6 from both sides. And I'm going to get d is equal to 7. So the answer is I have 6 quarters and 7 dimes. All right, does that make sense? I mean, you can check it, right? Remember, each quarter is worth 0.25. So if I multiply 0.25 times 6, that means I have like $1.50 in quarters. And each dime is worth 10 cents. So if I multiply 0.10 times 7, it means I have 70 cents in terms of dimes. If I add those together, I'm going to get my 220. So it's a good way to check it to make sure that it works. Okay, that's good for now. Again, in lecture, if you guys want to do more applied problems, we can certainly do that in lecture. Great, thanks.